Hello, good morning students. I am Dr. Kamanashish Goswami, Assistant Professor, Department of Electronics. Now today in this session we are going to discuss the excitation table in digital electronics. Now this excitation table is useful while we are going for designing some sequential circuit like counters or when we will go for conversion of flip-flop. In these cases, this excitation table is highly required. Now, popularly, what the students do is they simply remember, they memorize the table, but no need to memorize this table, the excitation table for any flip flop. Simply, we can determine or we can make the excitation table if we know the truth table of a particular flip flop. Now, what is flip flop? Flip flop is obviously it is an essential block for sequential circuit. It acts as a single bit memory. That means it stores one bit data. Either it could be 0 or 1. So if there is no excitation in input, no input is given further, then the data will be stored. Now if this particular data is known as present state. Okay. Suppose this is a flip flop, JK flip flop. This is Qn and this is Qn bar. These two are input for JK flip flop and these two are output for this JK flip flop. Now the present, suppose it is storing a data 1. Now and this data will appear at this output. This data at present is called present state. Now if we don't excite the input terminals or we don't trigger the input terminals further, then this data will be stored. Now, what if we want to store any new data? Then what we have to do? We have to trigger up the inputs or we have to excite the input terminals. Then some other data will be stored. The new data is called the next state. Okay. So, what is next state? The data a flip flop is holding. If we trigger the inputs or if we make some input changes in input, the new data will be stored. That new data is known as present state. These two terms, next state and present state, these two are very frequently used terms in digital electronics, especially in sequential circuits. And obviously, whenever we are talking about flip flops, another thing is required, that is clock. So, for our convenience, we consider clock is there. Clock is active always. So, for this session, we don't bother about the clock. It is there. We will assume it is there. Clock is there. Okay. Now, if we consider a 3-bit counter, okay, so 3-bit counter means we need 3 flip flops. The output of the flip flops are Q0, Q1, and Q2. Now it is 3-bit counter, that means it runs from 000 to 111, and then again it starts counting from 000. Okay. Now, what are these 000s and 111s? These are the output of 3 flip flops. The LSB is this one, MSB is this one. Now look at this particular flip flop and output of this particular flip flop Q1. Now with the sequential pulses, the output of the Q1 is changing from 0 to 0. That is, if this is the present state, this will be the next state. If this is the present state, this will be the next state, and so on. So we know if we want to design a counter, we know the outputs. So that means our output of 3 flip flop should be like this. Now we have to design. Okay. Now how we have to design or we interconnect the flip flop so that this sequence of output should come. Okay. Okay. So here the excitation table is required. Now we will start from the SR flip flop. Okay. So we know the truth table of SR flip flop. Okay. SR flip flop. To input S R, output Qn, and inverted output Qn bar. Oh, we don't bother about this Qn bar. Okay, because if we know Qn, we will know Qn bar. That is not a big issue. Now this is the truth table of a SR flip flop. If S and R are excited with 0 and 0, or 0 0 is given, the next state or next output, that is Qn plus 1, will be equal to Qn. That means we can say there is no change. Okay, no change means if it was storing 1, the next state will be 1. If it was storing 0, the next state will be also 0. That means there will be no change of state when the S and R both are 0. Okay. That is called no change condition. Okay. Now, if we apply 0 and 1, okay, then the output should be 0. That is, it will be reset. If it is 1 0, output will be 1. This is 1, this is 0. And this case we know, if we apply 1 1, this condition we cannot apply in case of SR flip flop. This is an undefined condition. Okay. Now we know the truth table of this SR flip flop. Now what we told is, if we know the truth table, we can calculate the excitation table. Okay. So in this case, we have introduced another table that is called characteristics table of SR flip flop. Okay, we will introduce this characteristics table for each and every flip flop. So what is that? It is nothing but SR flip truth table along with this one Q1, that is the present state. We have introduced or incorporated and one more column, that is Qn, which is the present state. Now in this case, whenever we are giving a input, suppose 0 0, we are saying there will be no change. That means the Qn should be equal to Qn plus 1. Now the question is, what was Qn? So Qn could be either 0 or 1. So we have considered both the cases. For 0 0 conditions, we have considered both the cases of the present state, that is 0 and 1. Okay. So like 0 0, for all these combinations, we have considered our previous conditions 0 and 1. Okay. So now look at this characteristics table. This is also important and easily we can make it from this truth table. So this is the combination S and R. Okay. So it is S and R are 0 and Qn is 0 for this yellow column. 0 and 0. Okay. Now if it is 0 0, that means output should not change. Okay. Output should not change means this one is 0, this output Qn plus 1 also be 0. Okay, fine. Is there any other 0 0 SR condition? Yes. This red one, first red column. See, this is also 0 0 SR. 0 0 SR means Qn plus 1 will be equal to Qn according to our truth table. So now the question is, in this case, when it was 0 0, SR is 0 0. Once we have considered 0, Qn 0. Now it could be 1 also. We don't know what is our present state. So if it is 1, what will be the next state? 1. Okay. So for first 4 columns, we have considered Qn as 0. And for last 4 columns, we have considered Qn, that is present state, as 1. And we have calculated or we have made the next state, that is Qn plus 1. Now from this characteristics table, we can calculate or we can determine our excitation table for this particular flip flop, that is SR flip flop. Okay, how? Now output could be changed from present state to next state. Next state is Qn plus 1. Now what could be the probable condition of Qn and Qn plus 1? It could be 0 before the input. It could be 0, next state could be 0, that is one condition. Previous state was 0, next state could be 1, this is another combination. Present state is 1, next state could be 0, that is another combination. Or present state could be 1, next state is also 1. Sorry. Next state could also be 1. So this is Qn and this is Qn plus 1. Okay, present state, next state. So there are 4 possible combinations of Qn to Qn plus 1. Okay. Now we will see for these 4 probable conditions of Qn to Qn plus 1. what should be the combination of input terminals, or what should be the combinations of input given to the input terminals, or what should be the combination of input that should be given to this input terminal, or input terminal should be triggered up or excited by this S and R. That is the input combinations. Okay. So now we have put this Qn in the first column of this excitation table, that is the present state, and this is the next state, that is Qn plus 1 of the SR flip flop. See, look at this difference. In SR flip flop, the inputs are given. Okay, the input combinations are given. We determine the output. But in case of excitation table, in each and every flip flop, the transitions are given. Okay, that means the outputs are known, whether it is coming from 0 to 0, 0 to 1, 1 to 0, or 1 to 1. What is the change? Now, according to these four possible changes from next state to present state to next state, we determine the combination of inputs, the logic combinations that should be given to the inputs. That is the difference of truth table and excitation table. Okay. Now look at this, the first column. In the first column, Qn is 0 and 0 is changing to 0. Next state is also 0. Okay. Now we have to find what are the possible combination of S and R so that it will produce a 0 when the previous condition also was 0. Okay. So to find this one, we have to check up this column, first column and last column. There is Qn and Qn bar. Okay. So where is 0 at the first column and 0 at the last column? This is one thing. This is 0. This is 0. And second one is this one, the yellow second row. This is 0. This is also 0. Okay, fine. So it is transforming from 0 to 0. Present state is 0, next state is 0. Now, what is the probable combinations of S and R? In the first column, first row, the S and R are 0. Both are 0. Yes, we know if it is 0, 0, Q will be equal to Qn plus 1. That is no change condition. And if you apply 0, 1, 0, 1, so output also be 0. So for both the rows, Qn, if Qn is 0, Qn plus 1 is also 0. Okay. Now for these combinations, for both the cases, S is 0. Okay, S is 0. But in the first case, S, R is 0. Here R is 1. That means we will take a don't care term. So this first row is done. That is for 0 to 0 transition. Our S should be 0 and R should be a don't care term. Now come to the next combination, that is 0 to 1. The present state is 0, next state is 1. So what should be the probable combination of S and R? Now let us find out. So where is 0 is transforming to 1. Now this is the row, green row. The present state is 0, next state is 1. Okay, fine. So what is the combination of S and R? S is 1, R is 0. Is there any other row where the present state is 0, next state is 1? No. So for this transition from 0 to 1, we can write the combination of S and R is 1 and 0. Fine. Now the third combination transition from present state to next state is 1 to 0. Now let us find out where 1 is transforming to 0. That is 1 is our present state, 0 will be our next state. So this is the row. Okay, where present state is 0, present state is 1, next state is 0. Is there any other row where present state is 1, next state is 0? Answer is no. So what is the combination of S and R? S is 0, R is 1. So S is 0, R is 1. The third combination is done. Okay. Now the fourth or the last combination is 1 to 1. Present state is 1. Due to some excitation, the next state also be 1. So for this required transition, that is 1 to 1, what are our possible or probable combination of S and R? Now let us find out where 1 is transforming to 1. This one, this red row, this is 1, that is present condition is 1, next state is also 1. Is there any other rows? Yes, the second red row, present condition or present state is 1, next state is also 1. Okay, Now we have to consider both the rows. Okay. Now look at the combination of S and R for both the rows, red rows. For both the rows, see here R is 0, but here in this case S is 0, here S is 1. That means we can put R is 0 and S is don't care term. So this is how we can get the excitation table of SR flip flop. Okay. And another thing we can determine, that is called the excitation characteristics or excitation equation. Okay. So simply we can solve a K-map and we can determine the equation for Qn plus 1, that is our output. Our inputs are present state, S and R. And simply by solving a K-map, we can have the characteristics equation of SR flip flop. Okay. So hope it is clear how we can have the excitation table and characteristics table for SR flip flop. Now next move to our next flip flop, that is JK flip flop. Okay. Now this is the truth table of JK flip flop. Okay. Only difference with the SR flip flop is, in case of SR flip flop we cannot use 1-1 combination. Okay. It produces a undefined condition. But in this case, we know in JK flip flop we can use this 1-1 condition. That means we can trigger up the J and K input terminals by 1 and 1 logic combinations. Okay. So the first three combinations, that is 0, 0, 0, 1 and 1, 0 of J and K, produce the same output, that is the next state, as just like our SR flip flop. Okay. That is for 0, 0, Qn plus 1 is remain unchanged, that is equal to Qn. For 0, 1, output is 0. For 1, 0, output is 1. But here for 1, 1, it is Qn bar. That means if Qn is 0, Qn plus 1 will be 1. If Qn was 1, Qn plus 1 will be 0. If the JK flip flop is excited with 1-1 logic combinations. Okay. Now, like the previous case, we will make this characteristics table. Okay. Just by introducing another column, that is the column of present state, that is Qn, and definitely like the other case, we will repeat the 4 combinations of JK, that is 0, 0, 0, 1, 1, 0 and 1, 1, 1 for 0 and present condition and 1 present condition, that is present state. Okay. And here are the table, excitation table. Okay. Now the thing is, we have to determine or make the excitation table. Now to fix up the excitation table, again similarly we have to check where are the 4 probable transition from present state to next state, that is 0 to 0, 0 to 1, 1 to 0 and 1 to 1. Okay. Now find out. Now for our convenience, I have already labeled with yellow color. This first 2 rows, see here, the present condition is 0, next condition is also 0. Now we have to check what are the combinations of J and K. So J is 0, see here, for both the cases J is 0, but here K is 0, here K is 1. Okay, that means we can write J is equal to 0 and for K we will go for a don't get condition, don't get term. Okay, so the first row is done. For 0, 0 transition, our job is done. Okay, this if you can take 0 at the J terminal and you don't care at the K terminal, so that we can have a 0 to 0 transition. Present state is 0, next state also will be 0. Okay. Now the next state is 0 to 1. The next transition actually 0 to 1. That is present state is 0, next state is 1. Okay. Now we have to find out where 0 is transforming to 1. Okay, I am using this term transforming. That is present state is 0, next state is 1. See these two terms, these 2 rows. Okay, labeled by green color. Present state is 0, next state is 1. Okay. Now we have to check out. Simple procedure. What are the combinations of J and K for both the cases? Here J is 1 for both the cases, but here K is 0 for the first row, and here K is 1. Okay, in the second row. So for these 2, 0 and 1, we have to go for a don't care term. That is what we have done. For 0 to 1 transition, we have taken 1 as j and I don't care as k. Okay. Now, what is the next transition? From present state to next state, that is 1 to 0. Okay. So this is third row. This is for 1 to 0. Now we have to find out where are the possible combinations of j and k for which 1 is transforming to 0. Okay. Okay. So this blue rows, present state is, look at this board, present state is 1, next state is 0. Here also present state is 1, next state is 0. Okay. So what are the combination of j and k? See, k is 1 for both the cases. So k is 1. Okay. What about j? Here j is 1, 0. Here j is 1. That means j will be a don't care term. That is what we have taken. J is don't care term, k is 1. Okay. Now what? Next is our 1 to 1 transition. Okay. Okay. So where 1 is transforming to 1, these two red rows. 1 to 1, 1 to 1. Okay. Now the next thing, we have to find out the combination of j and k. K is 0 for both the case. So we have put k is 0. What is j? Here j is 0, here j is 1. So j is a don't care term. So this is excitation table. Simply we made with the help of truth table. Okay. And this is a characteristics equation of this one JK flip flop. Simply by solving a K map for Qn, K and J, we can have this, we can get this characteristics equation. Okay. Next, move to our third flip flop, that is D flip flop. Okay. So we know in case of D flip flop, instead of 4 combinations, we have only 2 combinations. Okay, because the inputs are swapped with a diode, we know. Okay, that means we are not able to give 0 0 and 1 1 combinations in the inputs. Okay. So when D is 0, Qn plus 1 is 0, we know. When D is 1, Qn plus 1 is 1. Okay. Now here similar thing, we have introduced another column, that is with the truth table, that is our Qn or present state. So we have considered both the combinations or both the rows or both the transition thing from for present state is 0 and present state is 1. Okay. So when present state is 0 or D is 0, next state is 0. If present state is 0, this is 1, D is 1, next state will be 1. If it is 1 or 0, it will be 0. If present state is 1, if we apply a input as 1, output will be 1. Okay. That is, we know, that is the property of D flip flop. Okay. Data flip flop. Okay. Now look at the transition. 0 to 0, 0 to 1, 1 to 0 and 1 to 1. That is from, again I am repeating the same thing, that is present state to next state. So put 0 to 0, 0 to 0, D will be 0. 0 to 1, D will be 1. 1 to 0, D will be 0. 1 to 1, D will be 1. Okay. That is comparatively easier with respect to SR or JK flip flop. Okay. And that is the characteristics equation. We can have it from this table using a simple K map. Okay. Next is our T flip flop. Okay. So this is the truth table of T flip flop. We know. Okay. That is, in case of T flip flop, the input terminals are short. We know it. The input terminals are short. Okay. And obviously we have to take JK flip flop. Okay. So if we apply 0, 0 0 will be applied here. If we apply 1, 1 will be applied here. Okay, 1 1 will be applied here. Okay. And we know for 0 0 in JK flip flop there is no change. Okay. And for 1 1 the output toggles. That means Qn plus 1 will be equal to Qn bar. Okay. Okay. Now this is the characteristics table. Okay. For 0, it is 0. For 1, 0 is transforming to 1. Here it is 0. The input is 0. Present state is 1. So next state will be 1. It is 1. Present state also 1. So it toggles. That is 1 becomes 0. Simple thing. That is the characteristics table. We can have the characteristics equation similarly. That means by solving a simple K map. Okay. And now That is our excitation table. Okay. Similar thing, that is we have to go for searching the combinations of T for the transition of 0 to 0, 0 to 1, 1 to 0, 1 to 1. Okay. Here 0 to 0, T is 0, 0 to 1, T is 1, 1 to 0, 1 to 0, it is 1, 1 to 1, it is 0. Okay. So I hope now this excitation table, how to get excitation table is clear to you. Okay. Thank you.